Good day, class. Let us now continue our lecture. This time, let's focus on force resolution into rectangular components. Another way of breaking a single force is by using mutually perpendicular axes as the direction of the force components. Let's say we are given this particle acted by a single force with a given direction. To resolve this force, you may create two perpendicular axes which are coplanar with the given force, and you may label the axes as x and y and put those labels on the side in where you prefer to designate as positive. So for the horizontal axis, you may put here the x label to denote that forces directed to the right are considered positive while to the left are negative. Similarly, for vertical axis, you may put here the y label to denote that forces directed upward are considered positive while downward is negative. This given force can be resolved by drawing the rectangular components acting on the same particle. F sub x represents the components along the horizontal or x-axis, while F sub y represents the component along the vertical or y-axis. Notice that the length of the arrow lines are drawn in a way that a rectangular shape can be formed, with the given force as the diagonal of the rectangular shape. To show the formulas that you can derive from this example, we can first redraw this figure using triangle rule. You may apply the triangle rule to have convenient basis for deriving your needed formulas. With this right triangle, we can now apply the trigonometric functions and write cosine of angle theta is equal to f sub x over f, or frequently, this form is preferred during problem solving. In the same way, we can also write sine of angle theta is equal to f sub y over f, or commonly, this form is usually used or usually applied by students during problem solving. For the inclination, you can use the tangent function as follows and rewrite it into this form. Lastly, you can check the magnitude of the force components that you have obtained by solving the magnitude of the resultant using Pythagorean theorem and compare it with the given single force. Take note that these formulas are applicable for the specific orientation of forces. This means that for other problems, different formulas may be applicable or are applicable. These are another two examples out of several possible orientations of forces. Notice here on the right that angle theta is with respect to the horizontal. Therefore, its components can be expressed by the same formulas as before. On the left side, the given angle alpha is with respect to the vertical. So applying trigonometry, its components should be expressed as follows. Take note of the difference between these two figures about their needed formulas. If angle theta is unknown, then you can get it by this formula. In contrast, if angle alpha is unknown, you can get it by solving the arctangent of f sub x over f sub y. Again, notice the difference between these two formulas. To form the right formulas or equations that you will need, you must draw carefully the direction of the forces and be mindful of any given angle of inclination. As we did in the previous slide, you may draw a new diagram by triangle rule before applying trigonometry so that you will be guided as to what appropriate trigonometric function you should use and how you can formulate the needed equations. Although the orientations may vary from one problem to the other, the formula of getting the magnitude of rectangular components is still the same for all cases in two-dimensional situations. We can better understand this topic by going through with some sample problems. For our first problem, we have here a man pulls with a force of 300 Newton on a rope attached to the top of a building, and we are given this figure. What are the horizontal and vertical components of the force exerted by the rope at point A? Let's first write what is required. We are tasked to find the x and y components of the given 300 Newton force. This follows that this is about force resolution using rectangular components. We start our solution by idealizing the connection at point A as a particle and drawing the mutually perpendicular axes. Then, we label the axes as follows to denote that all force components that have either rightward or upward direction are considered positive, otherwise negative. Then we draw the position of the given force, represented by force F, and denote the unknown angle as alpha. Next, we draw the position of the rectangular components, making sure that a rectangular shape is formed with the given force as the diagonal. Notice that in here, the value of alpha is not explicitly given, but dimensions are provided in the problem, such as 8 meters and 6 meters. Using those dimensions, we can now get the value of alpha by solving the arctangent of 6 meters over 8 meters, which is equal to 36.87 degrees. Please take note that these two triangles in the problem and in our solution are similar triangles. Therefore, you may include in your drawing this ratio of the sides to guide you in getting the necessary angle of inclination or direction of a force. Now, to solve for components, let's use the given 300 Newton magnitude and apply the trigonometric functions. Based on our figure, we can write force F sub x is equal to force F times cosine of angle alpha, which is equal to 300 times cosine of 36.87 degrees. From this, we can have this positive value and conclude that the x component is equal to 240 newtons to the right. Similarly, for the vertical component, we write force F sub y is equal to negative force F times sine of angle alpha. A negative sign should be written since the direction of the force is downward. From this equation, we now have negative 300 times sine of 36.87 degrees. As a result, we obtain this negative value and conclude that the y component is equal to 180 newtons downward. Our next sample problem will include special properties of a right triangle. Before we solve that problem, let's just quickly review some of these special properties. Let's consider this right triangle and denote one of its acute interior angles as angle theta. Recall that in a triangle, the sum of two acute interior angles is 90 degrees. This means that the other angle is equal to 90 degrees minus theta. Another property is, from a right triangle, two similar triangles can be formed by passing a line from the right angle vertex to the hypotenuse perpendicularly. So in this figure, we can create this dashed line and divide the given triangle into two similar triangles. If we consider the right triangle on the left, we can also conclude that the other angle is equal to 90 degrees minus theta. Similarly, for the right triangle on the right side, you can find out that the other angle is equal to theta. Additionally, because these two triangles are similar, then their corresponding angles are congruent as shown in this figure. Please take note of these angles represented by theta because you can make use of these equal angles in solving problems involving an inclined plane. For our second problem, we are asked to resolve the weight W of the block parallel and perpendicular to the inclined plane as shown in the figure. Assume weight is equal to 50 newtons and theta is equal to 25 degrees. First, let's denote weight sub x and weight sub y as the required components. Take note that in the given figure, the axes are already given. Let's consider again the location of the axis labels as the positive direction. To begin our solution, let's write the given magnitude of weight, the angle of inclination, and let's make use of the given figure to draw the given weight and its components. Notice that this angle is also equal to angle theta, or the angle of the given inclined plane, based on what we have discussed in the previous slide. To get the magnitude of the x component, we write weight sub x is equal to negative weight times sine of angle theta. The negative sign is due to the direction of the force opposite to where the positive direction is designated. By substituting the values, weight sub x is just equal to negative 50 times sine of 25 degrees, or equal to negative 21.13 newtons. The magnitude and direction of this component can be written as follows. Observe how the direction is described for this force component. You can see here that a horizontal line was set as a reference in where the arrow line as the location of the force component is positioned at 25 degrees counterclockwise from the set reference for this component only. You may even confirm that by investigating the geometry of the drawing. W sub x is inclined 25 degrees from this horizontal line. Next, we get the y component by writing weight sub y is equal to negative weight times cosine of theta, which is equal to negative 50 times cosine of 25 degrees. Again, the negative sign is due to the direction of the force opposite to where the positive direction is designated. By substituting the values, we now get this magnitude of y component, and the final answer is expressed as follows. Take note that the direction now, or the reference that we set, is another reference just to conveniently describe the direction of this component. So in this component, the reference is set as a vertical line, while for this component is a horizontal line. So you can set different reference for the two different components so that you can conveniently describe the location of those components. The next topic is solving the resultant when more than two forces are acting on a point or particle, which we will cover on the next part of this lecture. So that's it for now. Thank you, class, and God bless.